Okay, we're going to now talk about the oral administration and trapezoidal rule equations on the equation sheet. So here's your oral absorption equation sheet. So this is when you have a single dose and the rate of absorption is greater than the rate of elimination. If the rate of elimination is greater than the rate of absorption, you cannot use this equation. And that's called a flip-flop model. I assume Dr. Basu had talked to you guys about that. But this is a non-flip-flop where the rate of absorption is quicker than the rate of elimination, which is usually the case, unless you're giving a sustained release or something like that. All right, so what I do with this one, or the way I think about it, is to really break up this piece of the equation. So this is a concentration again at any time t with, I replace that with t so that corresponds to these t's here. Okay, so your concentration at any time t is equal to your bioavailable dose. Again, this is one dose, not a dose rate, over volume. So this is almost like a bolus IV equation. It's just dose over volume. The bioavailability we have to consider now since we're giving it orally, and then pull out the Ka over Ka minus K. So what this does is it balances the drug going in, the absorption rate, and the elimination rate, and giving you that balance. Because remember, when Ka and K are in balance, that's when you get to your C max. And then you multiply that times 1 minus e to the negative kt. So that's your elimination rate constant. Or I'm sorry, what am I doing? Too much of the other thing, I guess. Don't do that. I'm going to just write it so I have room. E to the negative kt, that's your elimination rate constant, minus e to the negative kat. Remembering that these t's are whatever time period you're looking for after you've started or after you've given the dose. So you give the dose, it's going to come to a Cmax, and then it's going to start to decline. So this is going to be T after giving the dose, okay? This time. It'll give you that concentration. If you want to figure out the Cmax here, you first need to figure out the Tmax, don't you? So here's how you figure out the Tmax. Once you have the Tmax, you put that time T in to this equation, and that will give you Tmax. Okay? So it's not that hard. You just have to be able to plug all the things in. It helps me to separate these out because then I can kind of think of this as the dose effect, and then you're balancing the Ka, and that gives you your concentration at any time after you've given it. It's not a simple decay because this whole time you've got some absorption going in. We don't know when the absorption is going to stop. Even though we've got to the Cmax, that doesn't mean absorption isn't still going on here. It just means that during this time, the absorption is winning. During this time, the elimination is winning. Okay, and this of course is just another that bioavailability equation that we've used already. This means IV, this means non-IV. So you can just determine your bioavailability, or if you have bioavailability, you can determine whatever other thing you have using that equation. All right, and this is just your trapezoidal rule. And it's model independent. You don't have to know how many compartments there are. We didn't get into our multi-compartmental. I wish I could have, but we don't have time. So this is just this gives you your average concentration between the 2 points, which are the height of your rectangle. And this is your width of your rectangle. And then you just keep adding these up for all the rectangles, and this is the tail. Your last concentration over K, just like we've practiced before. And this is a model independent approach. You don't have to know that it's 1 or 2 or 3 or 10 different compartments. You can just use this equation to determine your area under the curve and therefore bioavailability, clearance, etc. Okay, hope that helps. Thanks.